Today we will discuss the aspects of vector integration, and broadly speaking, in vector integration we have a vector field where f1, f2, f3 are the components of the field along the x, y and z directions, and for the time being we will discuss the vector field in the Cartesian frame only. And in vector integration we deal with issues like line integrals and circulation, surface integrals, and volume integrals. After having introduced each one of them along with the corresponding evaluation techniques, we will be embarking on vector integral theorems. Now first, if you begin with the line integrals, it is basically connected to the problem of evaluating the amount of work done by a field. So suppose you have a field F in which we have 2 points A and B connected by means of a curve C. Then the amount of work done by the field in moving a particle from location A to location B along the prescribed curve can be evaluated using a line integral. Of course, the work done by the field can be positive, negative or 0. Particularly when the work done is 0, one has to be careful because there are very important implications of this particular situation. So let me start with introducing the line integral to you, how to evaluate it and what are the possible types of situations that one may come across. Okay, when we talk about line integrals, we basically require a field. So let us say this is a field and we have 2 points A and B connected by means of a path. We denote this by C. Now, the work done by the field from physical laws is given by integral f dot dr along C. Force into perpendicular distance measures the force. So therefore, measures the work. Now, if specifically f is f1i plus f2j plus f3k, the vector r is xi plus yj plus zk, then the vector dr would be dxi plus dyj plus dzk. Now when you take the dot product of this, you get the work done as the integral f1 dx plus f2 dy plus f3 dz. You can specify C or you can mention the endpoints A and B. Now this is the working formula for all line integrals. However, in order to get an output of this integral, the integration has to be performed with respect to a single variable, either in terms of x or y or z, or x, y and z all expressed in terms of a single parameter. Because the curve C would be described in the problem, it will be easy to convert this in terms of a single variable and integration can be performed. Now, in the other case, when the curve closes itself like that, then we introduce a notation closed line integral f dot dr, and this is called the circulation of the field. So basically in line integrals, we have open line integrals and closed line integrals. Whenever it's an open line integral, we just follow the simple way of integrating using this rule. And once the curve is closed, then we have two very powerful options with us to evaluate, depending upon whether C is in the plane or C is in space. If C is in the plane, then the Green's theorem option would be sufficient. On the other hand, if C is closed but in space generally, then we have the Stokes theorem, which will help us to evaluate such circulations. So we'll first look into the evaluation of open line integrals, a few varieties, and after that we'll go to the problems of circulation. At the same time, I would be introducing the Green's and Stokes theorem, so that we will explore all line integrals in one single place. Question number 1. What is the value of the line integral y square dx minus 2x square dy from 0, 0 to 2, 4 along the parabola y is equal to x squared? So this is the problem. As we discussed, to evaluate a line integral, we require to convert the integrand in terms of a single variable. So it is very convenient to express y in terms of x, and therefore this integration will become very simple. Now you can see dy can be written as 2x dx, and this would become y square becomes x to the power of 4 dx minus 2x square into dy is 2x into dx. So that way we have converted in terms of x, and the integration should take place within the limits of x, which is 0 to 2. So this would give us integral 0 to 2 x to the power of 4 minus 4x cubed dx. Integration is straightforward, x to the power of 5 by 5 minus x to the power of 4 from 0 to 2. So this will give us 32 by 5 minus 16, and this is 32 minus 80 divided by 5. So this will be minus 48 by 5. So you can see from the options that option C is the correct answer. So we have chosen a simple example by which one can understand how one must convert the integrand in terms of a single variable. So what is required is the endpoints of the curve and the equation of the curve itself. You can put it in y in terms of x or x in terms of y, depending upon the convenience of the situation. Let's go to the next problem. Question number 2. What is the work done in moving a particle in the field f is equal to 3x square I plus 2xz minus y j plus zk along the straight line joining 0, 0, 0 and 2, 1, 3. Now this is a situation where we have a straight line in 3D space. So we require the work done. Work done is always a line integral. So let's set up the formula. Work done is equal to integral f dot dr from a to b, and this is equal to integral 3x square dx plus 2xz minus y dy plus z dz from a to b. This is a, this is b. Now how to put in terms of a single variable? So you know from the geometry of 3 dimensions of straight lines, we can express the straight line in parametric form as x minus 0 by 2 minus 0 is equal to y minus 0 by 1 minus 0 is equal to z minus 0 by 3 minus 0 is equal to t. So this would give us x is equal to 2t, y is equal to t, z is equal to 3t. So dx is equal to 2 dt, dy is equal to dt, dz is equal to 3 dt. So this will help us to convert the integral in terms of the parameter t. Now, the limits for t can be obtained from any one of these three parametric equations. Suppose we choose y is equal to t, then when y is 0, t will be 0, when y is 1, t is 1. Therefore, the limits of integration can be taken as 0 to 1. In fact, you can get the same limits whichever parametric equation you select. So this integral will be integral t is equal to 0 to 1, 3x square, where x is equal to 2t. So you will get 12t squared into 2 dt plus 2xz. xz would become 6t squared, so that becomes 12t squared minus y is t into dy is dt plus z dz. Z is 3t into 3 dt. So one has to simplify this. Let us see how it looks like. This becomes 24t squared plus 12t squared minus t plus 9t. So this should make it 36t squared plus 8t. And you can find that this integration is pretty straightforward. Let us do that small calculation here. Integration of 36t squared would be 36t cube by 3. So we will get 12t cube plus integration of 8t is nothing but 8t squared by 2, that is 4t squared from 0 to 1. So this is 12 plus 4, which is 60. So this problem was selected to explain how you must build parametric equations for straight lines in three-dimensional space. The correct option for this problem is B. Let's go to the next question. What is the circulation of the field F is equal to y minus 2xi plus 3x plus 2yj about the circle x square plus y square is equal to 4. Now we know this is a circle centered at the origin and with radius 2. Because it's a simple closed curve, this line integration is called circulation. So the work done would be integral over C closed f dot dr. So this would be integral over C y minus 2xi plus 3x rather dx plus 3x plus 2y dy. It is here that the student will have two options. One is direct evaluation, number two using either Green's or Stokes theorem. I will explain both the things to you, but first let us see the direct evaluation. Direct evaluation requires conversion of this in terms of a single parameter, and that information must come from the equation of the curve. Now, for x square plus y square is equal to 4, that is 2 squared, the parametric equations are x is equal to 2 cos theta, y is equal to 2 sin theta, where theta varies from 0 to 2 pi. So this is the information. So we can convert the x's and y's in terms of cos theta and sin theta. At the same time, dx and dy should also get converted. So let us see. This would be integral 0 to 2 pi. Y is 2 sin theta minus 2x becomes 4 cos theta, dx would become minus 2 sin theta d theta plus 3x would become 6 cos theta, 2y would become 4 sin theta multiplied by dy would become 2 cos theta d theta. So this would become 0 to 2 pi minus 4 sin square theta. Then from here we can write plus 12 cos square theta. Then you have got the product terms, 8 sin theta cos theta plus 8 sin theta cos theta, that becomes 16 sin theta cos theta. At this point, we expect students to be thoroughly informed about the techniques of integrating such functions. Now, you know that from the range 0 to 2 pi, all terms containing odd powers of sine or cos would produce zeros. So, this term can be dropped from the integration. So, only these two terms will remain. So, let us see how we can quickly evaluate this. Whenever you have even powers of sine or cos, the range 0 to 2 pi can be written as 4 times 0 to pi by 2. So, this we can write as 4 times 0 to pi by 2 minus 4 sin square theta plus 12 cos square theta d theta. Again, if you can directly remember, 0 to pi by 2 sin square theta d theta is equal to 0 to pi by 2 cos square theta d theta is equal to pi by 4. This is a very direct result which students can remember. Then the value of this integration would be 4 into minus 4 into pi by 4 plus 12 into pi by 4. So, this is 4 times minus pi plus 3 pi. So, 2 pi into 4 is 8 pi. So, if you remember the conversion of Cartesian curves into their parametric equations, and if you are pretty good at remembering certain standard integration patterns, then it is very easy to compute these integrals. The correct option for this problem can be seen as D. But let me tell you, all circulation problems can also be attempted by either the Green's theorem or the Stokes theorem. In this case, I would like to also explain how the Green's theorem produces the same result but in a much faster way. But the only requirement is you must be able to remember double integration principles to do this problem. So, let me explain now how the Green's theorem can be applied to this. But first, let us write down the statement of the Green's theorem. It says, in the xy plane, if you have a simple closed curve which encloses a region R, closed line integral f1 dx plus f2 dy is identically equal to double integral over R dou f2 by dou x minus dou f1 by dou y dx into dy. This is the statement of the Green's theorem. So, given this, we can get that. And evaluation of a double integral sometimes is going to take lesser time compared to the direct integration. So, let us apply this to our problem. So, this is the field. So work done is equal to integral f1 dx plus f2 dy. Here this is f1, this is f2. So this would be identically equal to double integral over r dou f2 by dou x. So integrate this with respect to x partially and you will get 3 minus dou f1 by dou y, that gives you 1. This is nothing but twice double integral 1 dx dy. And all of us know that double integral 1 dx dy is nothing but twice area of this circle. The area of the circle is pi r square. So 2 into pi into 2 square. So that is how you get 8 pi very easily using the Green's theorem. So you can compare the earlier method with this method and you will find Green's theorem is definitely a good option provided the double integration is not that very complicated. So please remember, all circulation problems can be attempted by the direct method or by an integral theorem, right? Question number 4. What is the value of the integral f dot dr over c, where c this time is a closed curve, given f is equal to x minus y I plus x plus y into j around the curves y is equal to x square and y is equal to root x. So first we trace these two curves. Remember, this is also a parabola. Y is equal to x square is a vertical parabola and y square is equal to x is a horizontal parabola. So here the intersection points are 0, 0 and 1, 1. These are the two curves C1 and C2. But the requirement is that the motion should be anti-clockwise. So don't put clockwise arrow marks but anti-clockwise arrow marks. And you can see that a region is formed there, R. So as I told you, whenever you have a circulation problem, you can convert it using either the Green's theorem or the Stokes theorem. Green's theorem is always selected whenever the problem is set in 2 dimensions. Because this is a problem set in 2 dimensions, we can evaluate using the Green's theorem. So by Green's theorem, so what do we get? This is f2, this is f1. f2 with respect to x, so you get 1 minus f1 with respect to y, you get minus 1. So this is nothing but double integral 2 dx dy. Actually this is 2 times area of this region, but we are not sure what that area is going to be because it's not a standard region. So we'll actually perform double integration to get the result. So if you look at that region, R is an Rx region where x varies from 0 to 1. Y varies with this as a lower boundary and that as upper boundary. So y is equal to, this is the lower boundary. Lower boundary is the x square parabola and the upper boundary is the root x parabola. So you will get 2 times integral 0 to 1 x square to root x dy dx. So when you do this integration with respect to y, you will get twice 0 to 1 root x minus x square dx. So the integration of root x would be 2 by 3 x to the power of 3 by 2 minus x cube by 3, 0 to 1. So how much will we get? 2 by 3 minus 1 by 3, that is 1 by 3 multiplied by 2 is 2 by 3. So you will find this in the options. Option B would be the correct option for this. So please observe how the Green's theorem is simplifying the whole thing. But you know, in spite of having this advantage of 2 times area, we still had to integrate because we are not sure about how much that area is, because the region between 2 parabolas and its area is generally not remembered by students. And of course, it will not take much time to evaluate that small integration. So this is how one can evaluate quickly instead of going for the direct method. Going for the direct method would mean integrating over C1 separately and integrating over C2 separately and then adding both of them. So for exams of competitive nature, this option would be the best. Next problem. Question number 5. What is the value of closed line integral a dot dr where C is the circle y square plus z square is equal to 1, comma x is equal to 0 and the field is A is equal to 2xi plus 4yj minus 3zk. Nothing new about this problem, but students would normally get worried when they say equations, 2 equations like this. So I just want to solve this problem to remove the fear out of the students, saying that you don't have to much worry about this. This only means on the yz plane, because x is equal to 0 corresponds to the yz plane. On the yz plane, we have a unit circle, y square plus z square is equal to 1. So when you expand this, you will get 2x dx plus 4y dy minus 3z dz. And now we can introduce all the changes. You can observe from here, when x is 0, dx will be 0, which means this term can be removed. If you remove this term, you get 4y dy minus 3z dz. And don't forget, C is a circulation. Therefore, we can use Green's theorem. Only thing is, it's a Green's theorem in the yz plane. So this would be double integral over r dou f2 by dou y minus dou f1 by dou z dy dz. Okay, in the yz plane. In the xy plane, it would be dou f2 by dou x minus dou f1 by dou y. Right. So what do we get here? This is f2. This with respect to y and this with respect to z. So therefore, you get double integral over r. f2 with respect to y would mean 0. f1 with respect to z would also mean 0. So the output of the problem is 0, and therefore the correct option for this problem is D. Otherwise, the student can also do one thing. He can write y and z in terms of parameters. Y is equal to cos theta, z is equal to sin theta, and he can still be able to produce the same result. So the easiest way is to always react to Green's theorem or Stokes' theorem whenever the situation arises. Stokes, of course, is a slightly bigger thing, but Green's can be easily recognized. What is required for Green's is you must have a closed curve in 2 dimensions only, either xy or yz or xz. So this is another example where the Green's theorem is coming to extremely, for extreme use. So students should never miss opportunities to apply the Green's theorem. Question number 6. What is the scalar potential corresponding to the conservative field e power x into z minus bxy I plus 1 minus bx square j plus e power x plus bz k? Well, here we know that a field is called conservative if its curl is 0. It is already declared that the field is conservative. And we also know that whenever the field is conservative, we can find a corresponding scalar potential f or phi or whatever it is, such that the field is equal to f is equal to the gradient of that scalar potential. So let me put it clearly. Since F is conservative, basically the curl of the field is 0. This is one issue. Number two, there exists a scalar potential phi such that the gradient of that scalar potential is equal to the field. So now what is required in this problem is to find that scalar potential. But there is a problem. The problem is the field has got B, a scalar B in its components. So first we must get the numerical value of this B, then we must find out the scalar potential. So how do we get that scalar B? You must go back to this definition. So curl F is equal to determinant ijk dou by dou x, dou by dou y, dou by dou z of the components z e power x minus bxy, 1 minus bx squared and e power x plus bz. So we'll determine this, equate it to 0, then get B. That is basically the plan. So let's do it and see what happens. I times dou by dou y of this is 0 minus dou by dou z of this is also equal to 0 minus j into dou by dou x of this will give us e power x minus dou by dou z of this will give us again e power x plus k times dou by dou x of this is minus 2bx minus dou by dou y of this will become plus bx, and this is equal to 0. So these are natural zeros, and we get from here minus bx k is equal to 0. This would imply b is equal to 0. So what we now do is insert this b is equal to 0 into the field and write f is equal to, when b is 0, you get z e power x I plus j plus e power x into, and according to this requirement, this field should be equal to del phi. What is del phi equal to? Dou phi by dou x into I plus dou phi by dou y into j plus dou phi by dou z into k. So we can start equating corresponding components and determine phi. But you can see that phi will be generated in 3 different ways. We'll find all of them and take the union of that. So if you take this part, phi 1 will be the integral of z e power x partially with respect to x. So this would be nothing but z e power x. Then if you take the second components, phi 2 would be integral 1 dou y. So this would be nothing but y. Finally, if you take this part, phi is equal to integral e power x dou z. This will be nothing but z e power x. Like this, phi 1, phi 2, phi 3 are determined, and finally we must write the field, the potential. So the potential is nothing but phi 1 union phi 2 union phi 3. Now phi 1 and phi 3 are one and the same, so therefore we take it once. then to that you add y. But we cannot rule out a numerical constant c. Therefore, this happens to be the scalar potential. And you will see in the options that this appears in the location B. So, B is the correct option for this problem. So, what we have learned in this example is, remembering that when a field is conservative, first get any unknown parameters by taking curl f is equal to 0, insert that scalar back into the field and use this very important formula del phi is equal to f to determine the scalar potential. Let's go to the next problem. Question number 7. What is the work done by the field f is equal to 3xyi minus 5zj plus 10xk along the curve x is equal to t square plus 1, y is equal to 2t squared, z is equal to t cube from t is equal to 1 to t is equal to 2. This is a problem based on line integral. We got a field f 3xyi minus 5zj plus 10xk, where x, y and z are expressed in terms of parameters t square plus 1, y is 2t square and z is t cube, and the path is from t is equal to 1 to 2. So, let us evaluate this integral. So, f dot dr is f1 dx plus f2 dy plus f3 dz. 3xy dx minus 5z dy plus 10x dz. Now, we will have to convert this function in terms of the parameter t. So, the information available is x is equal to t square plus 1 implies dx is 2t dt, dy is 4t dt and dz is 3t square dt. So, introduce that into this along with x, y and z. So, we will have 3 into t square plus 1 into 2t squared into dx is 2t dt minus 5z, that is 5t cube, dy is 4t dt plus 10x, 10 into t square plus 1, dz is 3t square dt. So, this needs a little bit of simplification. So, this will be 6t into 2t square, that is 12t cube into t square plus 1 minus 20t power 4 plus 30t square into t square plus 1 into dt. So, this is 12t power 5, then t power 4 terms are coming here, minus 20 plus 10, that is 10t power 4 plus 12t cube plus 30t squared. So, it is now set for integration. So, let us look at integral f dot dr along c. This is identically equal to integral t is equal to 1 to 2 of this function, right, 12t power 5 and so on, 30t squared dt. I think all students can easily integrate this, simple algebraic integration. Be careful, upper limit is 2, lower limit is 1. Without much difficulty, you will get 303 as the answer, which is option C.